It's actually tough because it's the last day right before spring break, so I do appreciate actually you still make yourself available and come to the talk. So thank you very much. And also believe this talk will be very rewarding because we are going to learn a lot from Dr. Biswas. So hopefully let's welcome Dr. Biswas to give the talk first.
Yeah, I also really appreciate it, and thanks very much for coming. So I hope you find this talk interesting, and feel free to interrupt and ask questions anytime. You don't have to wait till I end. And I have this tendency to go over, so if you ask me questions before, I'll be good. So I just wanted to introduce my team. These are the people in computer science. So it's primarily me as a faculty member, and then John Kinnebrew is a research scientist who got his PhD working under me, but then has stayed behind, started off as a postdoc, and now is a full-fledged research scientist at the Institute for Software Integrated Systems. We have a set of grad students. Jim Segedi, the first, is going to finish, defend his thesis in another month or so. He has been working primarily in this particular environment called the Betty's brain system. I will briefly get into some of his work. I won't present that in any detail. Gautam Biswas is another PhD student working in the area of computational thinking. Kirk Lorenz has been working on an evolution of the Betty's brain project, and Cheng Ye has been working on data mining with us. I have a number of collaborators, but primarily those I shared joint funding with are Dan Schwartz, who's now at Stanford. He was at Vanderbilt before, and Roger Azevedo, who works on metacognition and self-regulated learning. We have a common grant from the Department of Education, the Cognitive and Student Learning Program. And then within Vanderbilt, I work very closely with, and again have joint projects with both Doug Clark, who works on game environments for physics learning, Pratik Gupta, who works on agent-based modeling and simulation environments and computational thinking. And then more recently, there's been a growing interest even within electrical engineering and computer science, primarily a push towards engineering education, but also towards this notion of combining STEM learning with computer science, the notion of computational thinking. So I've been working with Andy Gokhale on collaborative STEM learning, and then Vanderbilt is into these MOOCs. We are part of Coursera. We've run a number of these MOOCs. We have collected data, and working with a couple of other faculty in analyzing this data. And within another project within our institute is we've got a huge project from DARPA where we are building design tools for building vehicles, and we are turning around and then trying to use those tools again for engineering education, teaching undergrads design. So those are the variety of projects that I've been working on in this particular area. Very quickly, just to name some of the projects. So Betty's brain, I won't talk about much, which since that's what the focus of today's talk is, but it's been evolving into this system we call SimSelf in collaboration with Roger Azevedo. And the idea here is to move from just learning by teaching to a more sort of richer social environment where, say, you place students in a situation where they're working with multiple virtual agents. Some of them could be teachable, some of them could be peers, some of them could be mentors. And the question is, how do you set up these environments such that you can convey a lot of the self-regulation or metacognitive strategies to promote learning. And then I talked about the work in computational thinking, where we've shown through a number of experiments that students learn both the computational concepts as well as the science concepts much better when you try and teach both of these together than if you did them separately. We've extended that CT-SIM, which is computational thinking, using simulation and modeling, to this C3 STEM, which stands for collaborative community-centered, challenge-based STEM education, which we are primarily applying at the high school level, where we get them to actually model and work on real-world problems. Like currently, we are focusing on traffic simulation, and use that as a framework for in STEM learning. And it's deep STEM learning, so they learn the physics and learn to apply that physics and math concepts, calculus, and then use that for solving engineering problems. So example, look at traffic data in their neighborhoods or the neighborhood of their school where there's congestion at times of the day, and what would be their solutions to reduce this form of congestion. And eGame is a project that I work with Doug Clark at Peabody, where he's using game environments for learning physics concepts. So today's talk, I'll focus on Betty's Brain, which is really a generic name. When we first started, we gave the students the story that Betty was a middle school student just like them, and there was a river that ran by our house that was getting polluted, and she'd see these dead fish floating by, and so she really wanted to join the school science club to learn more about what the cause for the pollution was and how she could take care of it. And then, of course, the teacher said that she was just a 5th or 6th grade student, didn't know enough science, so she should be able to join. So the students' challenge was to teach her enough science so she could join the science club. And so that's how we started. And now, of course, we've evolved, so now students create their own agents, give them whatever name they want, and then they're interacting with the students. And it's very interesting to see the kind of agent students build. They look more like themselves. So they're creating their own likeness and then teaching them on the computer. So, and the idea here was, to make it really interesting and make it interactive. And to make it interactive, the agent had to do something. So as they taught them, the agent had to be able to use what they were being taught to answer questions. And so we created Betty as the ideal student who never forgot but never knew anything more than what the student had taught them. So, and then I'll talk about some of our initial studies. We'll talk about where we did seem to be doing too well, so we had the kids very much enthused. So we've changed our approach and are now thinking of the system more as an open-ended learning environment. And I'll describe what an open-ended learning environment is and what the advantages of thinking in that way are, and then show you some analyses we've been doing to understand students' learning behaviors, and then how we might scaffold and provide students to help them improve their learning processes. The goal of our work is, I'll describe it soon, as preparation for future learning, not just learning that particular topic that you're trying to teach them at the moment. So let me start by sort of contrasting what we think and what I guess most of you know is the traditional approach to learning, which very often in the science education literature and cognitive science and learning sciences is called shallow learning, where you're trying to get kids just to memorize definitions of concepts and facts and then just reproduce them in tests. So it's memorization without understanding. And whereas what we are interested in, if you're teaching science or mathematics, which is really applicable to the real world, what is more important is whatever little the student learns, they see its relevance to the real world and can actually solve real world problems using what they are learning. So that we call deep understanding, with the ability to generalize and transfer. And these have become big buzzwords now, for the 21st century workforce, this notion of lifelong learning, long-term retention. But what Dan and I came up with was this notion of adaptive expertise. And let me try and explain what we mean by adaptive expertise. So if you think of learning, right, you can think of it in a simplistic way as having two dimensions. One is efficiency, right? So you start off, you know very little, you keep practicing that particular domain like a car mechanic does, and soon they become expert mechanics. They haven't become expert physicists or expert engineers. They couldn't design a car, but with time they've become very efficient at what they do, right? So And then the other dimension is innovation. So this is what, say, researchers and scientists do. So when they start off, they know little about a domain, they explore, they probe, they come up with new ideas, and with time they're innovating and sort of discovering and creating or interpreting knowledge in different ways than what people have done thus far. And so if you are right down at the bottom and remain there for the rest of your life, you're a novice. Right? If you move along there, purely along the efficiency scale, you become what we call a routine expert. Right? And on the other hand, on this side, right, if all you're doing is only innovating, so any problem you get, you decide you're going to solve from first principles. It doesn't matter whether you solved that problem 500 times before, right? You're an eternal novice, right? You're not becoming very effective or efficient. So really, if you want to see ideally what we'd like to do is move students, it doesn't have to be the particular arrow that I've drawn, but some trajectory that moves them to becoming an efficient and effective problem solvers, but also innovators. When you come across new problems, you don't throw up your hands and say, I've never seen this before, right? So I can't solve it, but then try and innovate and find new ways to solve the problem given what you already know. So this notion of adaptive expertise, and we believe that in order to be an adaptive expert, you have to be an active learner. You don't stop learning. You know, as faculty members, as researchers, we've never stopped, right? There's new things coming up all the time, figuring things out, so you're always learning. You have to be constructivist, right? So you have to be able to construct solutions, and you have to be self-regulated. So you have to think of strategies, you have to have engagement, motivation, right? Otherwise, it's hard to achieve.
On this graph, are you collapsing efficiency and effectiveness and saying they're the same thing? If you move over to the right, you are in fact more effective?
Yes, but effective is probably sort of a rather high-level word, because you can be effective in this domain, you can be effective in that domain too. So I just threw out that word as a general term, but hopefully when you're here, you're truly effective in both of these domains, right? If you just move along this domain, you're efficient. Right? You're doing things better, faster, quicker. If you're moving along this domain, you don't let problems phase you. You take them apart, work them from first principles, but you don't want to do that for every problem you face. So trying to combine the two is what makes you an adaptive. It's a term that we use, an adaptive expert.
Can I ask another question on that?
Sure, please.
Do you view adaptive expertise as something that can cross the contexts, or is it within one context? Like in science is one context.
Yeah.
I mean, something else, like economy could be another context.
So that's a very good question, right? And you would say that a true expert might be one who's able to transfer from one context to another. But if you've gone and read the book How People Learn that John Bransford and others put together, you know that you take a physics expert and give them a social science problem, they'll be able to interpret the problem much better than a novice would. Doesn't mean they're going to come up with an expert solution to the problem.
Mm-hmm.
So there's a lot to expertise that has to do with domain knowledge, and it should not be trivialized. But just having domain knowledge is also not enough, right? So there are different components to expertise that are important. And what we are saying is, of course, when you're in middle school, high school, you want to have broader expertise. So when you talk about metacognition, self-regulation you can think to be domain independent. We are finding metacognition, though it's defined to be domain independent, in reality, you learn metacognition in the context of a domain. So it's tricky and difficult. So especially when you're trying to teach it to someone who's a novice, these things become big issues. You can't just say self-regulation is domain independent, so I'm going to treat it as a domain independent strategy. We tried that and it fell flat in the system. That students said, why are you telling us all this? It's of no use to us.
So is it possible that maybe it's safer to define all these in the context as opposed to across contexts? I mean, I'm just asking because I deal with the same questions, and it seems like there's an open-ended ongoing question whether
And I
things
think
can
it's
be
going to
transferred.
remain for a while, right? So,
For a
so
while,
in a
okay.
sense, if you're studying it from purely a theoretical or a research viewpoint, you do want to keep it as domain general as you can.
As you can, to be on the safer
Yeah,
side.
but
right.
on the other hand, if you're trying to sort of implement or build systems based on these principles, right, you need to think differently. At least
Okay.
that's what we've learned.
So
Thank
domain
you.
knowledge could be one of those elements within this entire system of innovation, efficiency,
Right.
if something is very novel,
Uh-huh.
or if it's something that you know very well
Right.
in terms of domain knowledge.
Uh-huh.
So I see multiple variables that you would be
Sure,
looking at there.
sure. And I remember I said this is an oversimplified representation of how people learn. We just wanted to drive home the point that there are at least two different dimensions. Rote learning is okay because it might help you become a routine expert, but it certainly doesn't help you on the other dimension. Right?
Mhm.
And so, but combinations of those are hopefully what we are looking for. So really the challenge here is, can we build learning environments, computer-based learning environments that support this notion of how to become an adaptive expert, and that's what we call preparation for future learning. Because we brought up this term of domain knowledge, right? That also isn't a static construct, right? So what we learned in computer science when I was a graduate student, right, would hardly get me anywhere nowadays in terms of the way the field has advanced, right? And if I didn't keep up with it, right, there's no way I could call myself a domain expert of any kind, right? And it's true for any discipline, including education, learning sciences, etc. So let me then switch to why we went to learning by teaching. Of course, you could go back to the literature, and there are a number of examples where so Bach and Schul was one of the first where they came up with this idea: teaching is a powerful way to learn. Mickey Chi, Art Grace, others have done a number of these protocol studies where they've studied tutor-tutee interactions, and they've come up with the conclusions that sometimes tutors learn more than their tutees through these interactions, right? And there's an interesting study that John Bransford and Dan Schwartz ran just before we started building these systems, where they divided up their class into half and told one half of the class, you go study this material to take a test. The other half, they said, you have to study this material because you have to present it to the rest of the class next week. And there was a very interesting dichotomy there in how people
Welcome to
learn,
the world of teaching.
right? So the first group, they finished, they said, oh, it took us about 45 minutes to an hour to read this thing and to be prepared. And we knew what quiz questions looked like, so we prepared for the quiz. But the second group spent hours and hours, and they were worried even when they came to class. They said, yeah, we are prepared, but who knows what questions we are going to get asked in the classroom, and we had to prepare for that. And as teachers, we've known that, right? I mean, we come prepared to class and a student asks a question and you're floored, because we never just thought of things in that particular way. Now sometimes the student's asking a very good question, that you have to go back, reflect on, and come back and give an answer the next time. Sometimes maybe the student's on the wrong track, but either case and even more, we learn a lot through these interactions. So most of us will admit that we've learned much more once we started teaching than what we learned as grad students or otherwise. So therefore, right, it's clear that teaching is a better way to learn. Students themselves, if you make them teach, are more motivated to learn the material more deeply because of this notion that they're going to interact with others. And of course, if you look at what teaching involves, and I was discussing this with Yeping earlier, that teaching is not just standing in front of a classroom and telling everyone what you know. There's a lot of effort that goes into preparing for teaching. And of course, after you've taught for 20 years, you've sort of figured that out and don't spend as much time. But early on, spend a lot of time making sure I understood the material, how I was going to structure it, how I was going to present it, and that itself goes a long way in terms of trying to get a much deeper understanding of the material. And then when you're presenting, right, you have to be ready to firstly you're observing your students. Sometimes you're saying things, and you know it's going way above their heads, and you have to pause, stop, right, rewind, probably go through the material again, present it in a different way. Other times, questions sort of make you think of things differently, right? And then very often what we are doing is at the end of the day, we are going back thinking about what happened in class that day. The next day next time you teach, you probably spend 10-15 minutes going over that material again, clarifying things based on what you think the students need. So you're continually reorganizing your knowledge in a way that you can present it and make it more understandable to others, and that's the key. So teaching involves all these great things, which certainly are very important if you're a learner too. So a lot of teaching is really learning for yourself.
That's so exhausting.
So how did we apply these principles? I'll show you, and since I don't have time, I won't do demos of our system, but if you're interested, that's the website from which you can actually download Betty's Brain if you'd like to. So just to get you started, right, so it's designed, the current version of the system I'm going to talk about is designed to help middle school students learn about science processes, so ecological processes, right, so predator, prey, pond ecosystems, fish tanks, and maybe notions of climate change, thermoregulation. So all science projects, processes are governed by this notion of interactions or interdependence between entities, and then this cycle where things are usually in balance because most natural systems have this feedback loops from using an engineering term, where if you perturb the system, it sort of comes back to an equilibrium situation. If you push it too hard, then it doesn't come back, right? And that's what's sort of happening in climate change. So here is what the system looks like. So we have this agent called Betty with the students teaching. That central area is Betty's brain. It starts off completely blank. She knows nothing. As the student teaches her, she learns exactly what the student has taught her. You can see how the student teaches. They're creating a causal map. In this case, they're teaching her about climate change. And the way they do it is all drag and drop, point and click. So they click on this, and if they click on the main screen, a box comes up, right, into which they can enter a concept name. If they if they click on this and drag the mouse from one box to another, right, they get a link is drawn, and then they have to fill in the name of the link and what the effect is. So will this increase something or decrease something? And so we make it simple for them. So there's an underlying qualitative reasoning scheme behind this. And then they have various other editing tools. And so they teach her, then they can get her to take a quiz, and they can also interact with her. So the student asks Betty to answer this question, and the greenhouse effect increases, what happens to global temperature, and Betty answers, and then the student can ask Betty to explain her answer. And then the idea is that by asking her to explain her answer, they'll see how she reasoned, because students aren't very good at reasoning initially, but watching how she does it, they learn how to reason, and what they're doing is they're teaching her the model that she's going to reason with. So here is how they know how well they're doing. They can ask Betty to take a quiz. She does. In this case, she's got 2 of her answers right and 3 of them wrong. What we really like students to do is focus on the answers that are wrong, find out why they're wrong. Sometimes they're wrong because it's because they haven't taught her enough, so she just can't answer the question. Sometimes they've added incorrect links. And you can see that as they build the map, this gets quite complex, especially if they haven't checked their map. Once they have 3 or 4 errors in the map, it's really tough to figure out what exactly those errors are and correct them. So a lot of the strategies we teach students are, hey, check your map as you're building it, not for every link, but small parts at a time, so that you're sure what you're building is correct, right, before you move on to building other parts. So from a design principle, right? What were the principles we used? So we teach through a visual representation. We obviously don't want students to become computer programmers to teach an agent. That won't work at all. So, it's a simple interface where they drag and drop. So the focus is on them learning the representation, what it means, right? What the implications are if you connect concept A to concept B and says, say A increases B, right? So what does that mean? Of course, they go beyond that because they may be creating this model in pieces, but they have to reason. So they may have created links from A to B to C to D, and then a question pops up: if A decreases, what's going to happen to D? So they have to figure it out by this chain of reasoning. Initially, they don't know how to do it. Betty does, so they observe her doing it, and then hopefully they learn in the process. So they're learning more of the science. Right, then it's built on these well-known teaching interactions where, when they need to, they can go read resources to find out, right, what knowledge they need to teach her, and they come back, have to create it into a causal form, they teach it, and then we can check whether she's learning. So they're presenting, interacting, right, in some sense they're teaching by telling her, right, they're teaching her how to model, they have to check, probe, etc. So all of these are activities that are important when you are teaching. And the last is, right, how do you make it a little more than just pure make-believe? Right, their agent has an independent performance. This has proved to be one of the sort of more important principles that I'll talk about on the next slide. So when they are getting the agent to take the quiz, it's the agent who's getting answers right or wrong, not them, right? The agent got 3 right and 2 wrong, right? But they are the ones now who have to help the agent to get the wrong answers, right? It's very different from telling a student in class that you only got 2 out of 5 on a quiz. It puts them off. They don't like to hear that. But if you tell them, hey, by the way, your partner got these things wrong, can you help them get it right? They love that, right? They love that sense of responsibility, like probably most of us do. And so one of the guiding principles, right, learning as a social process, is that we are using exploiting this notion of shared responsibility in keeping students engaged, in keeping students going back. So typically, what happens in a class, the teacher gives a student an assignment, the student does it as quickly as they can, turns it in, right? Teacher says, okay, here's what you got right and wrong. Student says, fine, I got 70%, right? I'm going to pass. What do I care about anything else, right? But here it's different, right? The teacher, she gets things wrong. They have to figure out how to get her to do things right, which means they have to try and correct their own knowledge. So this cyclic process is going on and on, right, till she gets all her quiz questions right. And these quiz questions are not the same, they're dynamic. We use this principle of zone of proximal development. We don't want to frustrate the student too much. So if they build part of the map and part of it is right, we always give questions that some of them are going to be answered correctly, some wrong, and the ones that are wrong, some will point to areas where they haven't still built their map and some where they made errors. So now that's what we do now, and so the students to figure that out and then figure out how to correct or build on their maps. And so the whole process, this notion of we call it self-other monitoring, right, is much more engaging and keeps the students involved than sort of being told, right, you're not good, you're not getting this right, and go study, right? So instead it's, how do I help my agent? So let me figure out, what she did wrong, and then I'll try and teach her. But in the process, they have to learn for themselves, and they have to do a lot of reflection. How do I get my agent to do things right? So then in the early versions, right? So how did we scaffold students' learning? So Betty was self-aware. So the way she interacted with students, she would come back and say, hey, you've taught me this. Can you really ask me questions to see if I really understand? So we made the dialogue pretty lively, right? So she would express a lot of joy if she got things right. She would sort of express some disappointment that she wasn't doing well in the quizzes. And that seemed to work well. So, and she would ask things like, did I get this answer right? and sometimes come back and say, I should learn more between quizzes. And this was directed at students who use this, guess and check method. They add a link, take a quiz, right? Decide how to fix it, add another link, take a quiz, which is not a good way of learning because they're just guessing. They don't want to go read the resources to figure things out. So she'd come back and say, I really don't like keeping on getting answers wrong, so could you do something more between getting me to take quizzes? And sometimes, she would refuse to take a quiz. You didn't teach me enough between quizzes. And we found that was interesting. So they would sometimes curse Betty, say, Betty's stupid, she just doesn't get what we are teaching her. But then they'd slowly come around and realize they had to do more teaching. And then I didn't talk about this, but there's a mentor agent. You saw the other person in the figure. He's comes around. He's sort of looking over what's happening, and every now and then, as we realize a student wasn't doing very well or was getting stuck, he'd come in and make suggestions. But he'd never just tell them, this is wrong, here's the correct answer. Suggest, hey, look, this part seems to be wrong. Why don't you try this, or why don't you try that? So the idea was to give the student strategies and guidance rather than just the correct answer. A lot of the tutoring systems that are built, what happens is, if the student gets something wrong, you stop them and say, this is wrong. And you give them 2 or 3 chances to correct it. You give them some feedback. Finally, if they don't get it right, you give them what's called a bottom-out hint. You just give them the answer so they can move on. And we found that that's very detrimental to learning. Because if you do that, and the students figure it out, and they're pretty smart at that, they're going to do arbitrary things till they get the bottom-out hint, and go on till they get the next one, and so on. So in our case, right, even if students get frustrated, which they do sometimes, right, they don't get these bottom-out hints. Right? Once in a while, we might as a reward to a student, but mostly not, right? So, and we learned early on that, like I was saying earlier, that you just tell students, try this strategy, it doesn't work. You have to sort of put it in a context, otherwise it doesn't work. And then we've tried to make the delivery more conversational to reflect a social process rather than, here is this computer system sort of spitting these things out at you. So just as an example of the kind of support the mentor gave, so think of this, right? So if a student got Betty to take a quiz and her score improved quite a bit, so the student had added 2 or 3 correct links, both the mentor and the mentor would come back and say, great work, right? So the last set of links you just corrected is good. So there's a lot of positive reinforcement in the system. But if, say, what happens is students got Betty to take 2 or 3 quizzes and there doesn't seem to be any change, so he'd come back and say, you're having trouble. And instead of saying, here is some help, we usually say, would you like some help? And it's perfectly fine if the student says no, because that means they're not ready to receive help. There's no point in giving it to them. Right? We ran this collaborative study once where 2 students worked on the system at the same time. We recorded their conversations, and very soon we'd see after 5-10 minutes the kids would turn the voice down, right? Mr. Davis's voice down, take off their headphones, and they'd tell each other, and Mr. Davis doesn't know what we are doing. He's boring us. So they'd set it aside and continue to do things their own way. So we learned soon enough that we had to keep them engaged, and the best way to do it was by putting things in context. And sometimes we let students ask questions too. And so student can ask what to do, and then the mentor would again in context say, what do you need help on? And students chose what they needed the help on, and then the mentor would provide it. So very quickly, one of the very first studies we ran was, say, somewhere in 2005, where we worked with, say, 2 classrooms of 5th grade students, and we created 3 versions of the system. So one was sort of the no teaching system. We call it the intelligent coach. It had the mentor, and so we told them they were learning for themselves. If you wanted to check how well you're doing, right, get the mentor to sort of give you a quiz, and you'll know how many you got right and wrong. So all those features were there, but it was done through a mentor. This was a baseline learning by teaching where it had Betty and the mentor and the mentor would again just give corrective feedback. You took the quiz, you got 3 right, 2 wrong, etc. We created a third version which, in addition to that, had this self-regulated or strategy learning feedback. And so the study, we had a main phase where students took a pre-test. They worked for 6 sessions creating a concept map on river ecosystems. They took a post-test, and then we did a transfer study too, where they worked on a second unit, but I'll focus on the results from the first unit. So these were the different conditions. So you see that the main features were all there. The difference was whether Betty was there or not, and what kind of feedback the mentor gave. So the system in which we call the intelligent coaching condition, there was only the mentor, but everything else looked the same. Yeah.
So I have a question about the use of concept mapping as the kind of teachable moment with the students. So like when we use concept mapping, we usually have them kind of identify the concepts to build the map based on a real experience or exposure to a phenomena. So they can kind of engage, so it's not just inert kind of words and links. Is there a piece of when y'all implement this kind of thing where they get to kind of engage? You said the previous one was the river model. Like
yeah, so initially they would have to enter the names of the concepts themselves. We found it to be really, really difficult because they make all kinds of spelling errors, right? And we were giving them feedback as they were working on the system. So really, in a sense, this looks like a concept map, but it's a very specific form of a concept map. It's a causal model that they're building, right? So there is more than the meaning of that this is connected to this. This is saying that solar energy provides, right, absorbed light energy. So the more sun you have, the more light energy will be absorbed by the earth, right? So that is really, there's a meaning to it, right? A very specific.
And where would they get that knowledge? From text?
From resources that they get, right? Or they know it themselves. Sometimes they know it themselves, but sometimes they have misconceptions in what they know. So you can see that. So for us, right? Now what we do is when they click on and say I want to enter a concept, we just give them a drop-down menu with a number of names, and they pick from it. Because you could say that is an important part of the learning process, but let's say we are skipping it. We are saying this is the topic you're learning, these are the set of concepts that you use, right? What we mainly focus on is building the links and the right model.
So you provide the concepts to them,
Yes.
right? Whether they have experience or not is not an issue,
So that
but
they're
you
doing
provide the
outside.
concepts.
So it's a part of a problem-based learning unit. So what the meaning of the concepts are, etc. The teacher is discussing in the classroom, right, in terms of a project that the students are working on. Here they're learning the specific content.
At least they don't come up with things that are not concepts and put into the middle, I guess.
Yeah, in the older versions of the system, they would. So when we evaluated their maps, we had to look at, was this concept even relevant to the topic that we were asking them to build, right? And did it appear in the resources, though we weren't looking for it in the map? So we had to do all those evaluations. Obviously, you can't do all that online. So we just decided to simplify it from that viewpoint. So we don't expect our system to be, take care of everything. We expect this teacher plays an important role in the process. So a lot of the background learning, what they have to know to build these models, the teachers also covering in the classroom. They have the resources on the system as a way of going back and checking, or if they've forgotten something to pick it up again. But we aren't claiming that we are teaching them this thing from scratch, this particular knowledge from scratch.
Do they work in groups?
So the next proposal we are writing, we want them to work in groups. We have made them work in pairs just to collect protocol data so we can analyze. I'll be talking about it soon, how we analyze their patterns of activity, and we want to see if our interpretations are the same as the way they think.
Is it because this Google's map building tool that's available right now that kind of your interest is in the group work as opposed to 2 people working together?
No, our interest is in, so even when we work on collaborative projects or collaborative map building, we'll first make them build their individual maps. And then we want them to come together, and there we are more interested in the critical thinking and the argumentation processes they go through. So we've done this before. So we got two students to build the same maps. We overlaid one on the other and said, yo, this part of your map is the same between the two of you. This part you did and he didn't do. This part he did and you didn't do. And still, even if you put it all together, you don't have the complete map. So how would you go about building the complete map? So we want them to start discussing with each other, right, and resolve things. And that's, if you are thinking of science as an inquiry process, that notion of critical thinking, right, and argumentation is as important as learning the facts themselves. In fact, it's more important than learning the facts themselves.
We did something similar in a professional development workshop with the earthquake engineering teachers, where they made their individual maps first. And then they had to make a group map. We were looking at how many people had accurate concepts in their initial maps, and then what the group map looked like.
Right.
And whether someone who had a lot of accurate concepts might be swayed to inaccurate concepts because of the group. And we videotaped, right, the conversations, audio taped them?
Audio tape.
Yeah, audio taped the conversations between the members of the group. And Baki is in the process of following what the individual concept mappers said for their individual concept maps, and then how that changed. We did the exactly same thing at the end of the professional development, where they developed their individual maps and then got together and
build a group map.
yeah. And I'm as interested in that social dynamic of what happens.
Yeah, we are too very.
Yeah.
Yeah.
Particularly for people who had the right concept at the beginning,
Right.
and then somehow in a group map, it goes the other way.
Yeah,
What are
because
the arguments?
someone else dominates the
Exactly,
conversation.
yeah.
And this person says, fine, you want to do it that way, and just accept.
So if you don't mind, another quick question. When you ask students to work in groups, are they going to sit in front of one screen?
Yes.
And so they will be connecting virtually on one map? I
No,
mean,
so
how
the
it's going
way
to work
we've done
with
it
more than
is-
2 people? I'm just wondering.
No, we want only 2, right, for now.
For now,
And
okay,
they will
pairs.
both work on the same. And when we've done it before, the teacher has told the student, you cannot add anything to the screen, right, till you have discussed it and you agree. And like you said, we are very much interested in that conversation or discussion that occurs, based on which they then come to a consensus that is what they're going to do. And in fact, there are times when the teacher has also tried this. He says, for 15 minutes you are in charge. You hold the mouse. You're in charge of the screen. Then switch over, and then the other student becomes in charge. So there are various such interesting models that we can study. We want to do it more formally. We've done this informally, mainly to capture the conversations. But now we actually want to study collaborative learning, mediated by
The real
technology.
challenge is, Carol said, the social dynamic of 4 students together is almost always there's one student
Yeah.
who dominates in some way socially, or, and their version of the map
Is what
may
takes
hold
over.
more sway socially. It's really tricky.
Yeah.
Uh,
And we're not trying to go there, right? That's what
Okay,
pays
I
on
see.
what we are saying.
yeah.
You can go first.
So when you talk about a complete map and try to see if the group can work together to reach the complete map, is that something like the final ultimate standard answer that you want them to reach? Is that
Which they never see, right? But only through quizzes they know that they have achieved that. So if they don't have the complete underlying quote unquote expert map, they will always get one answer wrong, at least one answer wrong. And the number of answers they get right or wrong is in proportion to how much of the correct map they have.
So you have like one single explanation for a phenomenon?
For a phenomenon, yeah. So that's a very good question, and you might say, but when we build models in science or engineering, we always sort of, if you just took engineering or science, there's no causality, right? It's based on set of equations where the relation between variables or concepts could go either way. But the moment you're solving a particular problem, there is causality involved because you're interpreting things in a particular way. And that is what we want the students to learn. Students will often complain, right? We say that if fish breathe, dissolved oxygen decreases in the water. They say, why can't we draw the link the other way around, right? That dissolved oxygen causes, right, increase in respiration in fish. And we tell them that maybe that's not in some other case that may be the right model to build, but in this case, right, we are looking for a very particular thing. We are looking at the interaction between the respiration process and how fish gain energy, right? So in that case, right, we want to think of it in this way. And so lot of the discipline in science and engineering comes with being able to interpret phenomena in a particular way and build a model that represents that, and then be able to reason with that model to solve problems.
And you might get into it here in a minute, but I was thinking along the lines of analyzing what they're doing. Do y'all have embedded into the software where it's kind of taking snapshots every so often? Okay.
Actually capturing every little thing the student does, and I'll explain that later. But so here were the questions we wanted to ask. Right, so do the students in the learning by teaching conditions learn more than say if they were just taught? Right, does strategy feedback further improve the learning performance? And do the students demonstrate the use of these strategies while learning? So I'll try and answer these one by one. So just as a start, right, we did give them pre and post tests that were made up of multiple choice and short answer reasoning questions. Right, an example of of a question is the one that's up there on top, where the science teacher told her that interdependence among things in a river is very important for the ecosystem. What is the meaning of interdependence? And give examples, right? And then we also evaluated the causal maps, right? So how many correct links they got, how many incorrect links they got, right? And then here is the answer to your question. We capture all of the students' activities, right? Every click in a log file. Not that we are interpreting every click. I'll explain how we interpret them later, but we actually have, so for example, you can see on the left that at the time this student did this, right, then did this, then did this. So we literally can replay what the student did afterwards, right, on the screen. It would look like exactly what the student did.
Well, I guess like my thought was if you could analyze the time lapse between things they got right, so you can almost see like, oh, they got 3 or 4 links right, and then there was a barrier, so you can analyze the barrier.
That's exact, and that's what we didn't do much of that before. We did have these heuristics where we said that for 5 minutes or 10 minutes, if the student isn't doing anything useful, time to intervene. But my student Jim Segedi, for his thesis, he's done much more precise timing, and we are using that to interpret, right, what the student is doing, and I'll discuss some of that later. But so here is the results of the pre-post analysis and the MAP scores. So the multiple choice questions, right, the learning by teaching group did somewhat better, but not really much better. The short answer questions, there was clearly a difference between those who were taught and those who learned for themselves, and the difference between the self-regulated learning group and the coaching group was significant, right? And then when it came to the MAP scores, the self-regulated learning group did significantly better than both the taught group and then the group that did taught but did not get the strategy feedback. And then when we looked at the correlations between these different components, there was a strong correlation between the short answer questions and the MAP scores, right? But not much between multiple choice and the MAP scores. So in terms of testing, it tells you, right, what's more important, especially in science. And the good thing was we could see that those who were better at building maps were also better at being able to reason and write down answers to questions in text, right, in explanatory form. So to your point now, right, we do collect every click, but to make the analysis more meaningful, Right, we divided up the students' tasks into it. They were either reading the resources, they were editing their map, which could be adding concepts, links, changing them, deleting them. Right, they might take a quiz, they might ask the agent a question, they might ask her for explanations. So the sequences of activities we are deriving look something like this. They did an edit at some high level, right? They did a read, then they went back, they asked a query, and so on. And from this, we are going to try and analyze the students' behaviors. But we do a little more, right? And because there's, if you just did it at that level, you're losing a lot of context, right? So when they're reading, right, what page were they reading? Now, of course, if you go down to too much detail, each action becomes unique. And then it's very hard to find patterns. So we have to find the right level of abstraction, and I'll talk about that in a minute. But here what we did was we decided that, we check if the action they were doing, right, the context was related to what they did before. So if they read a page and then added a link that was related to what they just read, we said that was a related action. Otherwise it was unrelated or irrelevant, right? And then, so these sequences then look like this: edit related, edit irrelevant, read, so on. Reads were always considered relevant, but so that way, and then we went about building these models, and I won't talk about how, that's more computer science, but here are the models that define the activities that these groups were doing. And these names like applied reading, uninformed editing, were derived from looking at the basic actions, right, and interpreting them in terms of actions that were next to them.
So it's Markov models.
These are hidden Markov models.
Yes.
that
And
we derived.
are they dynamic?
It's dynamic, right? Because basically it's saying that at the aggregate level, right, this group, right, is doing some amount of applied reading, and then there's a more chance that they will go to do informed editing versus, say, going into
Sure.
uninformed
No, I understand.
editing.
I'm just wondering if you tested any dynamic change in the model over time.
If we started doing that, so even
Be
if we did it
interesting,
here, like
yeah.
if we did a day 1 model, day 2 model, day 3 model, day 4
Yeah.
model, what would be the change in this model? Now we've given up on hidden Markov models because they are too aggregate. Right? We are more interested in following patterns of behavior in terms of the activities, and I'll talk about that as sequence packing. But here, just out of interest, you got these very aggregate models. It's clear that the group that got self-regulated learning had a much richer model. And you can see that the thing that the others did not have, right? This group did very little checking, this group did some checking, this group did checking as well as probing. And probing is checking and then looking at the explanations to see how an answer was derived in order to try to.
So may I ask
things out.
here, so you did consider all the elements that students did, not just related versus unrelated activities?
Yeah,
What-
everything. Right.
Okay.
So when we say uninformed editing, it's an unrelated edit, right? So what they did on their map wasn't related to the quiz they just took or what they just read.
So-
right? Whereas informed editing is related to something they saw in the quiz, which is related to the change they are making, or something they just read, and then they're building the map corresponding.
So
to
in
that.
total, like how many elements or like differences that students could do?
So there
like
are
5, 10
primary actions times 2, right? So each action could be related. Of course, we didn't consider reads to be unrelated,
Mhm.
right? Quizzes were not unrelated, but everything else could be relevant or irrelevant. So 6 plus 2, 8 in this case.
So
Okay.
did you have someone write the reading, they were reading, write the text that they were reading?
It's all done in an automated fashion.
Okay, so,
No, right?
Yeah, so when you said that they could, they could read and then they would edit.
Yeah.
Okay, what are they reading? Is it
They're
some-
reading the resources, which are a set of hypertext pages
Okay,
that
exactly.
contain the material.
Okay, so you would know where they were going and
Yes.
whether it was relevant or not
Yeah.
to.
Yeah, we didn't do eye tracking to know which line they were reading, but we knew what page they were on.
Okay.
And the pages are well structured. It's
Sure.
from middle school, so it's not like a normal textbook or a
Mhm.
research paper you're reading. It's well structured into topics and subtopics. Right.
So you could tell then
Yeah.
from which page they were on,
Yeah.
whether the change they made to the map was relevant or not.
That's correct. On that page, there might be 3 links, right, that are relevant to the map. So if they worked on any one of those 3, we'd say that it's relevant to what they read. And this is something we mark beforehand because the mentor uses it. Because sometimes a mentor might say, go read these specific pages, because he knows that these are the mistakes they're making. So let's move on. So this is just the definition of the different activities, but let me move on. So let me summarize, right, what our early results were. So we did prove, right, as early as 2005 that learning by teaching and learning by teaching by giving them some form of self-regulated cognitive feedback is effective, right? But we continued to do studies, and this is what we found. This was the study where we got students to, talk to each other. And we also later analyzed their logs and found that 77% of the feedback statements they got, right, they were ignored by the students. Right? Either they just click it off or they criticize what the mentor was saying and then click it off. And we were not new, right? So there's been a lot of work in these kind of open-ended, complex learning or problem-solving environments where researchers have found that students find about 20% of the feedback they get to be effective. So 80% of the work you've done is good, right? Or is waste of time. But so we went about figuring out how to fix it. So these are the 4 principles we adopted. That what you tell them should be aligned with their goal. Now that's a difficult task because we aren't asking them what their goal is. So we are interpreting it. It has to be relevant to the last set of actions they did, right? And it should integrate cognitive and metacognitive support, and I'll revisit that later because our initial idealistic principles were, hey, we teach them strategies, they'll become great learners. Little bit did we know that they lacked the cognitive skills to become metacognitive. So we have had to slowly build those kind of features into the system, where we often drop them down into tutorials and say, forget the task of teaching Betty, let's practice this first, right? And once you get proficient, go back and try to teach Betty, rather than them getting frustrated and doing nothing for 3 of the 5 days, right? At least they're learning something there, right? That's useful to them. And then this notion of we're building up more and more on this, trying to be conversational, trying to be natural in the interactions, and we have papers that discuss that. So let me switch to now. So there was a somewhat radical, it's not radical, right? We were always constructivist, wanted students to learn by exploration, by inquiry, etc. But our interpretation of the system has changed now. I mean, it's still a learning by teaching system, but the focus of what we are looking at has changed. So here is our interpretation of what a open-ended learning environment is. Right? So it is based on constructivist theories. You want students to construct and test their knowledge. That hasn't changed, right? But learning involves, right, actively constructing one's own meaning using prior knowledge and the experiences, hopefully, from our system. So they're learning by doing, right? We are not telling the student that you shall build the map this way. We say, here's the task, right? And here are a set of tools, right? Figure out how you want to go build it. But we want to monitor what they're doing because not everyone is good at doing that. So when they aren't doing well, you have to come back and guide them. So we provide all these opportunities, right? But we very well know, right, that so still, right, we provide these contexts and a set of tools for accomplishing the task. But here is our initial understanding of what happens in that question. We provided all the tools, right, for this person to eat spaghetti. There's a knife and the spoon, right? But they still eat with their hands, and that's what they do, right? So the point is that unfortunately, right, when you're working with non-experts, right, students who are novices, right, they can pose significant challenges, right? Because it puts a high cognitive demand. Like they have to be regulated, right? They have to try to learn material, right? They have to put it into a form that makes sense. They have to verify and check whether they're doing it correctly or not. That's not a trivial task. It's not easy for us when we are learning new material leave alone for middle school students, right? And so it's been reported in the literature that metacognition is very important because it differentiates people who go on to college from those who don't, right? Those who are more metacognitive, self-regulated are traditionally the ones who then go on for higher studies. Others don't. But the problem is that right, the self-judgment abilities, especially in middle school, are not well developed. Students lack prior knowledge, right? And they're poor at forethought and reflection. And they often underestimate their own, underestimate the effort it would take to do a task. And that's what causes frustration. If you thought you could do something in 15 minutes, at the end of 45, you haven't gotten close to finishing what you were doing, I mean, anyone would start feeling frustrated. So how you self-regulate and realize was not a 15-minute task and you really need to do more is important, right? That's part of the self-regulation process. So how do we imbibe that through our system? So now the way we look upon the system is something I've been saying, but was somewhat implicit. So we've divided the tasks the students do into three very explicit ones, and they are well separated in the system, right? So there's the information seeking, this is what I've been telling you about, right? There are these hypertext resources, very well organized, right, that the students can read. So for example, but they're not trivial, right? The climate change topic has 31 hypertext pages of text and images, right? So, and the map that they built has about 25 concepts or 20 concepts and about 26, 27 links. So for a 5th, 6th grader, that's a lot of work. Yeah.
You said earlier that the questions that are posed to Betty through the quizzes are linked to the zone proximal development for the person who's interacting with Betty.
Right.
Does the texts change to match what you would anticipate their reading level to be based on it as well?
Currently not, because we are not reading experts.
Okay.
Right? We've tried to use the Kincaid scale and get it down to the level of middle school language, right? But we are not reading experts, so I would never claim that we would know how to truly address that problem, other than by providing support which says, these are the kinds of sentences you should pay attention to. This is how you interpret a sentence and build a causal link. But for people who are poor readers, right, the system is always going to be a problem.
The other question I had was, you had mentioned at the beginning the 21st century skills, and as teachers and educators, we have to kind of change our paradigm to say, I'm not here to teach a child content anymore. A lot of times I'm here to teach them how to evaluate resources. And so in that regard, like us giving them 50 hyperlink text that we've already pre-selected, we're almost kind of taking away their ability to go explore and differentiate if something's valid or...
That's a very good point, but you have to start somewhere, right?
Oh, yeah,
you don't
yeah.
start by saying, you have to learn this, and here's the wide world of web for you to go find all the information, right? So therefore, right, the idea here is, don't tell them that the answer is in this page or this page, right?
Yeah.
Give them that, get them to learn the process of exploring, finding, building, understanding that they're making mistakes, correcting. And you hope that these skills will slowly generalize. So when we say preparation for future learning, our long-term goal, which we have got nowhere close to, is to say that we are teaching them enough skills and strategies that even outside of our computer environment, when they go back to working with paper and pencil, there are going to be strategies and approaches that they take away that they're going to apply. Right? Of course, that requires longitudinal studies, a lot more studies, and we'll have to collaborate with others to do that, because as a group we don't have the resources to do that. I have no intentions to grow my group.
One thing it seems to me that eventually would be very useful would be to put in trash knowledge and get them to compare faulty, poor, badly done stuff, which they're going to find on the internet anyway,
Right.
with what being provided anyway.
So as we
it'd be
get
a
to
great
the
goal to move towards.
as we get to this more collaborative learning, we intend to do. So in this case, maybe it would overwhelm the student a little to do too much of that. But when students are collaborating with each other, that's when you can sort of give them a little bit. Let's say someone picks up on it. How do the two reason that this isn't quite relevant for the topic that we are?
And the other thing is when you design a system like this, I mean, you can observe one teacher for an excellent math teacher for a year and collect everything in the world. And there are people I know at NSF who've done that, and that they will offer that room of stuff to someone to look at. But it was because there was not forethought on what are the variables that are important to us in this study that will enable us to have a platform upon which then we can build next. And if you have such a formidable task ahead of you that, oh yeah, we need to do resources, we need to do this and this and this and this, all of a sudden, you have so much data, and even a computer can. Yeah, so there's got to be a choice of variables, and that's very difficult. It's how to decide which things are important here. Like, there could be a lot more environment scaffolds than 3.
Yeah,
those
there
were
could.
the 3 that you guys chose to be most important.
Right, for now, right? I mean, you can
For now.
always build on this model. But we also wanted to make it clear to the student through the design of the system that these are 3 important components. In the previous version of the system, it was a little mixed up, right? Whereas here, when they are reading, right? Then when they are building, right, this is what the interface looks like. So they have the interface for building the map. And then when they are checking the map, right, this is what it looks. They still have their map, they have the quiz, right? They can go back and revisit previous quizzes, and they can ask for explanations which are sort of marked up the way are with the blue arrows, right? So they are doing that. So to them also it's clear that there are 3 primary activities they're working on, and they can switch between them. And it's become much easier for us to interpret what they are doing, right? Previously, if they had the resources screen up and the map building interface next to each other, we didn't quite know whether they were actually reading or they were doing something else, or they were talking to their next person sitting next to them. Right? Even now we don't know that, but at least, right, we know that when they're reading and not building the map and so on and so forth. And so that's been important. So how do we, I'm running out of time. I don't know what. What should I?
You continue a little bit. How many more slides you have?
I could go on for 10-15 minutes, but I can cut it down. So should I go on for 5 to 10 minutes?
Yeah.
Okay. And I'll rush a little. So I'll skip some of the details. I'm assuming all of you know what metacognition, self-regulated learning is. So the key is that it's both awareness, regulation, and reflection. And the other thing is people like Vansford and Zimmerman and others have shown that these kind of properties are very important to sort of determine, right, how successful students are going to be, as much as, say, their academic grades, right? So they've shown that people who are more metacognitive and self-regulated, as I said earlier, are the ones who are likely to go on to college rather than stop. So how do we monitor this? So we have built this model, right, and this is again sort of applying an AI model to it. So typically in AI, when you build planning systems, you have a set of goals, you plan, you execute your plan, you are monitoring your execution, right? If it requires changes, you make changes. And after a while, you stop and reflect on what you've done to see whether you are being effective or there are changes you need to make to your strategies or approach. And this continues for a while. So now, right, given that's our model, how do we analyze what students are doing in the context of the model? And that's where this notion of sequence mining comes in, right? So where we are looking at these activities students are doing and trying to sort of find common patterns of behavior, right? And then we try and interpret what those patterns mean. And so let me jump ahead. I'm going to skip this slide, so this is more a computer science slide which says, but I would focus on this, right? Because how do we now still capture enough information in our actions that there's context, but it's not sort of too detailed that it's hard to find patterns. And then, so here, that's how we do it. So the way we decide common patterns, there are 2 ways. So one is you look for frequent patterns in a group, right? And let's say if about half the students or more do it, you consider it a frequent pattern. That's just a heuristic. Another thing is when you compare two groups, you look at on the average how many students in group 1 do it versus how many in group 2. And that differential tells us, right, this is the difference in behavior within the groups. So that those are the kinds of algorithms we use, right? So that's the computer science aspect of it. But here is where how we decide, right? So we log data at this level. So when someone adds a concept to the screen, we know exactly where they put it, right, etc., etc. So if we know their screen locations, we know when that action started, if they completed it, how much time they were on it, if they canceled that action, right? So let's look at an example. So let's say a student is adding the concept carbon dioxide to their map. So we can note that they added this concept at this location, right? Or we can just say they added it near another concept called vegetation. Or we can say they just added this concept. Or we can say, right, they added a concept to their map. Or we can say they edited a concept, or we can say they edited a map. So here are the different levels. Now, which one is the right one to choose for doing our analysis is the question, right? So we've typically stuck to, say, this level, right? And said, we want to differentiate between adding, deleting, changing, but let's stay at this level. And then sometimes they may do a series of similar kinds of actions. So instead of recording each one, we say that there are multiple occurrences of this occurred. And then let's say we keep the notion of relevance and irrelevance, though we have gone beyond that. So in general, you could get examples like this, that they added a concept, right, no, they didn't add a concept. This was a concept which was removed, but it was relevant because probably the quiz said that this link wasn't right, so they were removing the concept so they could get rid of the link. Or they could say that this link was added, it was relevant, and they added multiple of these links. So that's how we define things. And then the way we study students, we decided the first study we were going to do was contrast high performers versus low performers. Are there differences in behavior between the high and low performers? And let me give you an example, right? So here is where, right, if I look at a student, right, the number of edit actions they did and how their map score changed over time. So this is a high performer. In the end, he ended up getting all of his concepts right, but even a high performer makes mistakes. Right? They're not always doing things that are right. On the other hand, this person is a low performer, added a bunch of wrong links, figured something out, for a while did fine, then really got back. So in the end, they had more wrong links than correct links on their map. So their map score was negative. So
Depressing.
it's depressing to see.
How many students? Did you collect data from in
So
total?
every time we run studies, we work with at least approximately 100 every time. But all this analysis is not done by hand; it's done offline. I'm just showing you some of these plots so you see, right, what the extent of performance of these students are. Right? And so we, in this case, we analyzed the data for 40 students from the 8th grade. We characterized those, so remember 15 was the max score they could get on the map. Those who got more than 11, about 16 of them did, right? And then those who had scores of less than 6, about 18 of them did, and the others were in between, so we decided not to consider that. And if you look at various measures, right? So link accuracies of the links they added, right? How many were correct at that attempt? So for the high performers, 60% of the time they had it correct. For the low, it was 42. How many actions did they have to perform to get a correct link? 11.6 versus 20. How relevant were the actions? So when they were adding things, how relevant was it to previous actions they did? And you can see each one of these has a significant difference in the two groups. But the other thing is that it's not that it's a cakewalk for the high performers. 60% of the time, 40% of the time they're adding a wrong link, but they're having to correct it. And many of them are doing it, right? So you can see that it's a complex problem. that they're figuring out how to solve and learning in the process. Right? It's not that they have prior knowledge and say, oh, I know this, and build the map. Rarely do we see a case where someone adds all the correct links, so they have a linear line which says, got it right. So, and then here when we looked at their patterns of behavior, I'll just summarize them for you, right? So the high group, right, the big difference between the high group and the low group was after a quiz, they were able to go back to the right pages where they had wrong links and read those pages. And that may be a reason why they were able to correct those particular wrong links. Whereas the low group, when they did it, right, they went back to read, but most of the time they were reading pages that weren't relevant to the errors they had on their map. So they could not connect the two. Right? So that was one big difference, right, amongst others that we saw. Right? And then the other thing about the high group was, if they added a link that was irrelevant or incorrect, they were able to remove it fast. And the way they did it was, they had this thing called, they added a link, took the quiz, right away realized that wasn't a good link and removed it. And so the big difference between the high and low performers is, the high performers don't end up with too many errors in the map, the low performers end up with a lot, like you saw the low performer. And then it's very hard to debug their maps, right? Because almost everything is wrong, right? Or quite a bit of it is wrong. They can't identify what is correct and what is wrong.
I think it also points out that the need for feedback is pretty high.
Right, and they were getting feedback in this case, right? This was a previous version of our system, and it's not that, in this case they were paying more attention to the feedback, but still they weren't able to use it very effectively. And I'll come back to that.
Do you ever have teachers who work with you do this? Do they go through this themselves?
We provide them with all the statistics at the end of the day. And
I mean, do they do Betty's brain the way the students do?
Yeah.
They do it.
Yeah.
And
they're very much aware of what the students are doing and what the implications of what the students are doing are. Because they worked with us for a sufficient amount of time that they have a good understanding. They've helped us create the curriculum.
it just occurs to me that this whole process is being done with novices.
The students.
Right. It is the assumption that experts would all have a graph straight up.
Very few, unless they were really truly experts in their domain.
Yeah, I mean, it's interesting, isn't it, how some people get to expertise through the hard way, through trial, error.
Yeah, but developmentally, you're looking at kids who don't have really skilled metacognitive
Right.
abilities at this time.
They don't inherently have it. They have to
Yeah,
develop
it's not there yet. It's not learned, and they probably have not had any opportunities to even employ them if the teacher's always telling them.
That's exactly the point, and I think that is one of the biggest advantages of the system. And a teacher who goes along with that and says it's fine, right? You can make errors, right? But let's learn how to correct them, rather than you made this error. I'm going to tell you the correct answer. Give you a slap on the wrist and move on.
Or, and one way we do that at math, and math is giving partial credit.
Yeah.
So the teacher can see, and the student can see where the error is.
Right.
And every time when it comes to this point, look what you do here.
Yeah.
How are your fractions? Oh, you don't do fractions very well? Well, look here.
Right, but the problem is when the teachers do it in the classroom and they're grading paper answers, right? They don't have as much details as we have of
You
what
guys
the
have
student
fabulous
did.
stuff.
And our teachers are sort of, they're thrilled to get this information. This time our teachers wanted to know of the total time the students spent on the system, what percentage was on reading, what percentage was on building, what percent was on correcting, right? And they're going to go back and discuss this with the students. That better be balanced, otherwise you're not being a good learner. Right? Even at the high level, you can see that's information that the teacher would never have unless you can use technology and make it happen. It's the importance of technology. So just very quickly, since I'm running out of time, since reading was so important, we focused on reading, and here we introduced time. So when they were reading a page, were they just flipping through it, or were they actually reading it? Did they go back and read pages, or was it the first time? We introduced that as additional characterizations of read. And then when you look at the high versus low, right? So this group is rereading to inform their map edit. So they read, they spend more time on their reading, they go back and make correct changes to their map. This group, right, they're taking a much more systematic, much less systematic approach, right? They're doing a lot of short reads, right? Don't seem to be getting much from the reads. And even when they do full reads, they don't seem to be related to other actions they've done. So, I mean, it seems obvious now, but it's great to see this in reality, right, in concrete form, right, that good students do things this way, or learn to do things this way, versus some never learn, and they are the ones who really need to be taught how to learn better. So, let me wrap up. Other things we've done is, of course, knowing what patterns are good. It would be great to know how these patterns evolve over time. So we've done that work too. So, for example, we can say that, you know, when do they do best in reading and adding a correct link? On the average, that happens most in the middle period, right? And it tends to decrease towards the end because the map gets more complicated, and so it's harder for students to add links. When you look at, you know, how much do they use the quiz and the explanations to try and figure out what's wrong in the map, hardly happens in the beginning, starts happening more towards the end. So that's good for our system. There's something they seem to have learned from it, and so on. And then we can also do this differentially, where we give different kinds of feedback to see, you know, when different groups would do things. And those who got more feedback on how to construct the map, right, tended to do more of that evenly. Those who got more on monitoring the map tended to do that more evenly. So this is more like, you know, because it's complex, we've now given them features where we say, if you think a link is correct, you can go check it off as correct. So, and then we wanted to see how many really use that feature. Those who got that feedback to do that tended to do it more evenly. This group didn't do it much before, started to realize it was a useful feature towards the end, started doing it. Right, and then here is another one on reading and taking notes. Here you see that this group tends to do it more evenly, but more in the beginning because note taking at the end is not so important, right? Whereas other groups have differences in behavior. So we can track all this, you know, and put it in this form that makes sense to a teacher. You're not just dumping a set of numbers out there. So let me end by quickly talking about where we are now. So now, right, we have got to the point where we think that we can, you're asking, right, so we can build a dynamic learner model. We can see how their behaviors evolve over time, right? And the key idea here, because I'm out of time, I won't go through the slides, is we've realized that we want to teach them strategies, but very often they don't have the skills that they need to implement their strategies. So that's when we've started dropping down and saying, hey, if you aren't doing too well, right, let's see if you really understand the skill. When you read, can you find links? After you've taken a quiz, can you identify where the link is wrong? Let's drop down to that, right? Practice that, then come back and learn. And so, you know, the whole idea is now that we have enough experience, right, we can define patterns of behavior, interpret them in terms of a model, right, and use that to generate more adaptive and dynamic feedback for the students. So that's what we're working on now. My students just finished a thesis in this area. I didn't want to steal his thunder, so I'm not presenting those results, but it's at a very interesting point. So we've used task-driven analysis. We have a model. These are the metacognitive strategies, the cognitive skills. These are the tools, right? We've created relationships between them so that we can interpret what they're doing in the context of this model in determining the feedback. Now, the interesting thing we've done is we've come up with much sort of more precise metrics, right? Effectiveness of actions is when they do an action, does it lead to an increase in the MAP score or not, right? So the more effective they are, the more. The other, in terms of the information generation, every action they do generates information. So when they do a subsequent action, how much do they use the previous information? So that is called support. How much support an action has. So we can actually measure that as we go along. And the third one is coherence. When they've done a set of things, right, how related were they to each other, or were they jumping all over the place? So we can use these measures to actually characterize students. And we started doing that. And my student, just to give you a little, has figured out that there are groups of students who are systematic, but under systematic there are subgroups, groups of students who are guessers, right? All they do is guesswork, and there's groups of students, right, who just get lost because they just don't have the cognitive skills. Right? We're able to detect that by clustering them on certain behaviors. Here's another very interesting thing we're able to do. So you would think on the one hand, adding an incorrect link, taking a quiz, removing an incorrect link is an effective guess and check strategy. They guessed, they saw that what their guess wasn't good, so they removed it. You study that in terms of these measures, they break up into 4. There's informed checking, right? That's the best interpretation of this. Sometimes they're guessing and checking because it's related to what they're doing, but they don't have immediate support for having done this. So it's not as good, but it's an effective guess and check because they removed that incorrectly. And then you have these two, when it's informed checking, it's supported, but they end up removing the wrong link. They end up removing a correct link instead of the incorrect one. And the worst case is this guess and check. Arbitrarily adding, arbitrarily removing, hoping that someday if you did this, right, monkey on a typewriter can type out the Shakespeare's works, right? So that's what they're doing. This problem is complex enough that they don't get the solution. Right? So let me stop right here. Right? So that's so just as a summary, right? We think these combined data and model-driven approaches we are beginning to work on is really powerful for interpreting students' behaviors online. We are getting to be more accurate in our online monitoring. Our adaptive scaffolds are becoming more effective as we collect all this information. Right? I just talked about this, that we want to now extend our learning paradigm to more collaborative learning. And the other interesting thing is we are providing teacher support, and I'll end with this by showing you some examples. Right? So here is what, right, you can track. So here is a student's map early. This is how it changed, and that's late. So a teacher can follow an individual student's progress. Here is the class as a whole. And this is extremely useful for end of the day. Why is it useful? Because the thicker the link, the more students have used it, right? So if the teacher can identify parts of the map where the students are doing quite well, but he can also identify parts of the map where a number of students have made an error. And so what we believe is that technology by itself is not the answer, but technology supporting the teacher. So the next day the teacher can say, before I work on the system, right, let's put up a map with this link in it. Let's discuss it in front of the classroom, right? And I think that's much more effective than just saying that, we are going to give some feedback and help the student do better, right? So that's what we are working towards. Here is where I'll stop. So here are profiles of 4 students who worked on another system. So there were students who do this.
You did have someone who went straight.
Yeah.
Wow.
In a class of 100, there are 1 or 2 students who are so smart, right, that either they're very systematic, so one read and they get it, or they have a lot of prior knowledge, so they can just build it. This is an interesting case.
Yeah.
I call it linear progress, but then they got stuck. Can you interpret this for me?
Are there like 3 students there, or?
No, it's 1 student.
Okay, what are
So
three
they got
dots?
to 13, which is so they
3.
had all their correct links. Why did they not complete the map? Why didn't they get a perfect score?
They probably had an IQ of over 100.
Because they had a few incorrect links.
Oh, I see. Incorrect,
Right?
correct, and
This
what are
student
middle?
never figured it out. His incorrect links never went away. You know why this happens? Because they think they have the right prior knowledge. They will never remove these links because they believe that that's the absolute truth. Everything else could be wrong except those few links because they have imagined that to be true forever.
They're stuck with
Yeah.
what they think is the truth. All right,
Yeah.
correct.
So yeah, and in this case, sometimes maybe our system can help them, but it's so much easier for a teacher to come in and say, "Hey, let's have a conversation." So here is a bad case, right? The student never did very well. In the end, added so many incorrect links, right? That the overall map score went back. This is the most interesting.
Yeah, it
case.
is.
How do you interpret this one?
Wow.
They
Oh,
cleared
light
everything
bulbs.
Start it
off.
over.
Yeah, this
Yeah.
student got so frustrated,
Yeah.
he deleted his entire map, right? And therefore got rid of the incorrect links, built it again, but still had a few incorrect links. Again got frustrated, completely deleted his map.
That's a style.
Something, a light bulb struck, like you said. The third time
Yep.
he or she didn't add any incorrect links and got to the right answer.
Well, and the x-axis, what are the numbers represent?
Those are the number of edits, the
Okay.
map, the map building, map correction.
107 edits of
Yeah.
work for
Yeah.
tenacity is
Yeah.
what that word.
Yeah, and you appreciate this, so you would say that, give this poor student a break, right? Come in somewhere here and say, you've been working hard, you've done a great job, let me help you a little, right? Rather than getting them to do this, right? So now you can see, right, that just monitoring the student and collecting relevant information can be tremendously useful and much more for the teacher than for us. Right? For us, it makes interesting talks and maybe it's good research, but ultimately, this is the driving force that can change the way we teach in classrooms. Right? And you can't blame the teacher with 30 students if you expect them to monitor students at this level. A teacher cannot do it. It's not humanly possible. So we can make technology make this happen. So stop right here. Apologize.